Today, we're making hinges. And yes, I know that doesn't sound very interesting, but I promise it's a fascinating topic because these aren't any hinges. These are hinges designed for space. So you always hear in the space community that space is hard. And I mean, obviously it's hard, everything's up there in orbit, but like, what are the details that make it hard? And today we're gonna look into that a little bit by designing what seems like a really simple device. A hinge, a thing that opens and closes. There's a surprising amount of complexity when designing a hinge because you have all these different considerations you have to keep in mind that you just don't deal with when you're opening a door here on Earth. I designed 4 hinges and ended up building 3 of them, and each had kind of a different design philosophy, and we'll talk through the pros and cons of the different designs I came up with and which one I like the best. Heyo, future editing breaking taps here. I thought I would break in for a moment because I realized I spoke for like 40 minutes without really talking about what the hinge is for. So in short, you can imagine this hinge being used for like a solar panel deployment mechanism. For example, this is Alba Orbital's Unicorn Pocket Cube. It's like a small version of a CubeSat, and you can see the solar panels deploy, and each solar panel, is connected to the next with a pair of hinges. So that's kind of what we're doing here. We're making little hinges for little solar panels on little satellites. Okay, back to the video. This is the first design that I came up with, and it has a basic hinge shape. There's an outer section and an inner section held together with a pin through the middle. There is this torsion spring, which allows the hinge to automatically open for deployment. And then you can see there's a stop down here so that the 2 halves only can open to 180 degrees and then they'll naturally stop. For this design, I had 2 main criteria kind of top of mind. I was concerned about ease of manufacture and thermal coefficients. And so to that end, I designed this to be all out of a single material. So this was supposed to be all aluminum, both the inner, the outer, and the pin through the middle. And by making all the materials the same, there's no mismatch between the thermal coefficients of expansion. When it heats up or cools down, everything will kind of stretch or shrink at the same rate. The retention method was planned to be just a simple press fit. And the way this works, if you're not familiar, is that one side, in this case the outer leaves of the hinge, have a diameter that is slightly smaller than the pin diameter. So you can see there's kind of an interference here. And then the inner section was slightly larger, so it was free to rotate. And then you literally take the pin and just kind of shove it through the hole, and it will plastically deform some of the metal and basically get retained by being stuck inside of the hole. So I thought this was very clever because it was all one material, so the thermals were fine. The press fit would have made assembly very easy. You just align everything, use like an arbor press, and press it together. Now, unfortunately, when I started to share this around and talk to people that know things about space, they pointed out a few major and fatal flaws. The first is that press fits are just not a very reliable method for space. During launch, that really high vibration load has a tendency to work press fits out. The other major flaw is that all of the materials are the same material. And now I know I just said that was a good thing because all the thermal coefficients are the same, and that is true. But the downside is that during launch, we're going to have an aluminum inner half of the hinge and the aluminum outer half of the hinge rubbing on each other violently due to the launch vibrations. And there's a high likelihood that when this is folded up like that, so when this is folded up and kind of stowed, the inner and the outer halves will bounce against each other and rub. And if this starts to rub together, they might cold weld. And cold welding is a phenomenon where if you take 2 metals that are sufficiently similar and you push them hard against each other and like rub so that you can get through the native oxide layer on the aluminum, then in the vacuum of space, the metals don't really know that they're separate parts anymore. They just see like, hey, you're aluminum and you're aluminum, so like, let's be friends. And they actually just weld together. Now I should note, we'll talk about this more later. There are ways to get around the cold welding issue with like coatings and lubricants and stuff like that. We'll talk about that in a bit. Okay, so that was, a fine first attempt, but clearly showing some inexperience with designing space hardware. So with the whole like cold welding vibration thing top of mind, I decided to go with a ball bearing hinge for the next iteration. Because I was thinking about it, I'm like, okay, well, there's always going to be a problem with a pin, because the pin will always be touching, the two halves of the hinge. So you always have either galvanic corrosion issues if you got two different metals, or you've got cold welding issues if it's the same material. So why don't we just skip that by using ball bearings to bridge the gap between the inner and the outer, and then you can choose bearings that are like silicon nitride or some other ceramic, and you have no cold welding and no galvanic corrosion issues. So that's kind of what I was thinking when I designed this setup. You can see it is a little more complicated than the first one. There's these two torsion springs. In an ideal world, this would be a single, combined double torsion spring. I couldn't find one of those that fit my requirements, so I ended up trying to make one myself, and it kind of worked, it kind of didn't work. But let's hide these for now. If we look at the hinge itself, it's made of 3 components. There's kind of a outer assembly that bolts together. There's this middle assembly that goes in between. And if we hide one of it, you can see there's a race in the middle for bearings. So there's a bunch of little ball bearings that are on either side of this middle section. The cross section of this hinge, the inner section has a race cut out, and then the 2 outer sections have races cut out, and they're held together such that the bearings are keeping everything separated, so it's only bearing on metal contact. And then you can see there's an additional feature that I added here in the back. There's this kind of hook-shaped looking thing. This serves 2 purposes. It's supposed to hold the torsion spring, so this spring will loop around the back, and that's the retention mechanism for the spring. And it also serves as a latch. So if we rotate this 180 degrees around after the hinge is opened, you can see that the little hook section here catches on this sheet metal component in the back, and then basically forms a self-latching mechanism. So once it opens, it's unable to bounce backwards because it'll hit this sheet metal and latch itself open. So that is this design. It technically works. So it assembled. The torsion springs are not very good because I had to take 2 regular torsion springs and bend them together, and it's a little janky, so you kind of use your imagination here. But in theory, if the torsion spring was a combined double, I think it would probably work. The tolerances are not great. You can see there's a lot of slop between kind of the inner and outer sections, so that would need to get tightened up for a more production-worthy sort of hinge. But the bones of it seem like it would work. The big downside here is it's just a lot bigger than I expected. So, I mean, I know it's a small hinge, but this is supposed to be designed for a CubeSat or a Pocket Cube satellite, and so every millimeter matters. And this ended up being actually quite large, and I wasn't expecting it to be so large. There's also a design flaw, which is kind of obvious in retrospect, and I don't know why it didn't occur to me at the time. But if you'll notice the assembly, the bearings are being retained by these 2 bolts in the back, right? So they're bolting these top 2 components together, but it's away from the center of rotation. There's no bolt going through the exact center in between all the bearings. And so you can imagine if you would take this hinge and kind of pull on it, it's possible that those 2 plates might open up a little bit and allow the bearings to escape, and then your hinge is completely come apart. You could, of course, fix that by putting a bolt through the center of rotation, but there's not a lot of space in the center here. And so even if you use like an M1.5 or an M2, there's not really enough meat there. So you'd have to make the race a little bit bigger or use smaller ball bearings. And it kind of makes this whole thing even chunkier than it already is. So if we iterate on the ball bearing concept and make something that looks a little more like a normal hinge, meaning it has a hinge pin, but still uses ball bearings, you come up with a design that looks something like this. This design has 3 main pieces. There's an inner hinge, an outer hinge, and then kind of like a retaining piece, which helps bolt everything together. And then importantly, there's now this hinge pin. The pin is what's known as a shoulder bolt, and this is basically just a bolt. So it's got threads at one end and, a hex drive at the other, but it has a really long shoulder that's reasonably precise diameter and surface finish. And you can use the shoulder bolt as like a rotation mechanism. So the bearings will actually ride on that shoulder bolt. We do a cross section. You can see that there are small bearing races cut into the inner and outer halves of the hinge. This means that the bearings will ride against the steel shoulder bolt as well as the two halves of the hinge and keep everything separated. So we're still relying on the bearings to keep the metals away from each other. So like silicon nitride bearings with aluminum inner and outer hinge parts and a steel shoulder bolt. And the reason we have this third component is because we need something to... Why did you do that? I don't remember why I did that. Oh, it was for assembly reasons. Right. It took me a minute to remember why I did it this way. Right, so the reason we need a third component is purely for assembly or manufacturing purposes. So we've got these races, right? And we need to get the ball bearings into the race before we assemble kind of the next part that sits on top of it. So if you made a single monolithic outer section and a single monolithic inner section, you can't put those together and also fill it with ball bearings. And so the compromise I made was having a third component that included the last race. And this allows you to assemble things kind of in order and then add this cap at the end and bolt everything together. There are also these little pockets that are milled out basically just to reduce weight. The material there doesn't contribute significantly to the strength of the hinge, so we can just get rid of it. And then over here, there's a little pocket that's milled out, and that's mainly so that there's clearance for this bolt in case it sticks through a little bit. Assembly of this hinge is definitely more complicated than the first one, but before we can even assemble, we need to talk coatings and lubricants. I didn't bother with this on the last hinge, but with this one, we're gonna try to be as faithful as possible. So most hardware that goes into space that moves has some amount of coatings or lubricants or both added to them to help keep things, sliding freely. So in this case, I'm first burnishing on a thin layer of tungsten disulfide. This is a dry lubricant. It's basically very thin platelets of what's known as a van der Waals material that likes to slide against itself. It has a low coefficient of friction with itself. This is also a reasonable defense against cold welding because you no longer have metal on metal contact. You just have the dry lubricant rubbing against itself. So tungsten disulfide is used, molybdenum disulfide, hexagonal boron nitride is also used. I think sometimes graphite's even used. There's a lot of different dry lubricants you can pick from. They all have pros and cons. So that's kind of the first layer of defense against friction and cold welding and galvanic corrosion. But it's not a super robust defense. So there are plenty of papers and a lot of hard-won experience in the industry showing that under high vibration loads, the dry lubricant can pretty easily get rubbed off. So from talking to folks, it's not uncommon to apply a vacuum-rated, space-rated grease on top of your dry lubricant, just to provide a secondary kind of insurance policy. There's a little more prep we need to do before we can assemble. The shoulder bolt that I'm using has a reasonable spec for diameter tolerance, but it basically has no specification for surface roughness. It's not bad, but it's not great. So to help with the surface roughness, make it a little smoother, more polished, I'm going to hit mine with some 1200 grit sandpaper. I'm also going to coat the pin with the tungsten disulfide. And then finally, I'll add a little bit of Loctite to the end of the thread. And there's one final thing that we're gonna do, and this was a tip that I got from Adam the machinist. Thanks, Adam, this was a really good tip. These torsion springs are kind of crunchy. Like they don't feel great when you're actuating them. And so a tip that Adam told me is if you take some diamond slurry, or in this case, silicon carbide polishing grit paste, and you put it on a thin piece of brass and run the brass and the polishing paste through the center of the torsion spring, you end up lapping the interface between the torsion coils to a much smoother profile, and it just gives a much nicer, smoother actuation. You don't have this like gritty nature anymore. So this was a really good tip. I'm gonna start doing this for all torsion springs that matter, because it's really night and day difference between the feel of a polished and lapped spring versus one that you just get out of the bag. So with all that prep work out of the way, we can finally start to assemble the hinge. I'm going to stand up the shoulder bolt and the outer portion of the hinge on a piece of putty. Then we just very carefully start loading in the ball bearings. These are 1/32 of an inch ball bearings, which is 0.79 millimeters for the metric folks. I'm using steel bearings just for testing, but for the real thing, you'd want to choose some kind of ceramic to avoid the aforementioned issues. Once those are loaded, we slide on the inner section of the hinge and the torsion spring and repeat the process with the top bearing race. After that's been loaded with bearings, finally we cap it with the third kind of additional extra component that screws into the shoulder bolt, and that is the finished and assembled hinge. Now, obviously that was a bit of work, so this kind of gets a C- as far as manufacturing and assembly goes. It's pretty tedious to do, and it feels like it'd be pretty easy to mess up as well if you're making, say, a dozen of these in one batch. The hinge feel itself is not bad, but it's not great. It's a little crunchy still, which is mainly, I think, a problem of the bearing races. So normally ball bearing races are hardened steel bearings, which we have, but then the material they're running against is usually also hardened. And in this case, it's just aluminum. So this is a major kind of downside to this particular setup, is that the bearing race is a soft material. And that can lead to like dimpling or denting, where the bearing kind of pushes into the softer material and leaves a mark. The other major design flaw of this... Hello, it's me from the future. My camera stopped recording yesterday and I didn't notice it, so everything from here on out I get to do again, but that's fine. There are two additional details that the savvy viewer might have noticed that I haven't talked about yet, and one's kind of important, one is less so. So the less important item is galvanic corrosion potential concerns. So the hinge is obviously made out of aluminum, but the shoulder bolt is steel. It's a stainless steel, but it's still a steel. So you've got two dissimilar metals that are touching each other, and over time in the right environmental conditions, this can lead to galvanic corrosion. Galvanic corrosion is the process when you have two dissimilar metals touching each other in the presence of an electrolyte. It basically forms a battery. And so one side acts as an anode and the other is a cathode, and you have a chemical reaction between the two metals and you get corrosion or like rusting at the interface between those two metals. The amount of corrosion depends on which metals you're using. So different metals have different kind of galvanic corrosion potential. Further apart they are on this chart, the more they will corrode each other. Now, unfortunately, if we look at the chart, we can see that stainless steel, in our case, we're using an 18-8 shoulder bolt, which is basically a 304 stainless, is pretty distant from aluminum on the chart. So there is a decent chance that if an electrolyte becomes present, we might see galvanic corrosion between this shoulder bolt and our aluminum hinge. This is something that you can control, right? So we can keep it in a dry and clean environment where there's no electrolyte and then there's no corrosion. So corrosion only happens when you have an electrolyte between the two interfaces. So if we keep everything dry and clean and humidity controlled, like in a clean room or a well-controlled lab, not an issue. We can also potentially mitigate this with more coatings, so more dry lubricants or some type of PVD coating that's applied over it. We could even potentially anodize the aluminum, and that will put a thicker oxide layer between the aluminum and the stainless. There's pros and cons to different choices, but it's something that you can mitigate with a little bit of planning. Unfortunately, there's a bigger flaw to this design, which I didn't think about at the time, but potentially could be catastrophic to emission. And it's again related to the materials that are used here. The shoulder bolt is steel and the hinge is aluminum, and now we have a thermal mismatch between the two materials. The thermal coefficient of expansion for aluminum is about 2 times that of steel, or stainless steel in our case, meaning that as the temperature rises, the aluminum part of this hinge will grow twice as quickly as the steel parts. So for example, if the steel bolt grows 20 microns, the aluminum is growing 40 microns. And if we don't have our tolerances sufficient to compensate for that, we could get into a situation where the inner or the outer half of the hinge expands enough that it pushes on the shoulder bolt and finds itself in a position that can't open once we get on orbit. All right, that's enough said about this particular hinge. Let's look at the final design, which I think is the winner for a number of different reasons. So this hinge, from just looking at it, doesn't look too dissimilar. It has the same general shape. There's obviously a shoulder bolt kind of pin going through the middle. We've got the same torsion spring. The hinge outer and inner leaves look pretty much the same, but there's a big difference in how it functions, and that's namely there are no ball bearings. Instead, there's this thin little spacer or bushing that everything's riding on. So here's what the little spacers or bushings look like, and those provide the interface between the hinge and the shoulder bolt. And this solves a couple problems for us. These bushings are made out of a Teflon and graphite-filled PEEK material. This is an engineering polymer that's rated for space, so it has very low outgassing characteristics. It handles extreme temperatures very well, from low to high temperatures. It doesn't get too brittle. It's not quite as strong or stiff as aluminum, but it's pretty close for a polymer. And then this particular variety has both Teflon and graphite in it, which means it's naturally kind of slippery. It's a low friction material. Also, it's just kind of weird, like when you hit it against itself, it sounds... It doesn't sound like plastic. It's a strange material to work with. It's also crazy expensive. This bar was 1 foot, 12 inches, half-inch diameter, and it cost $40. So yeah, you don't want to use this stuff if you don't need it. In any case, the reason we're using this bushing, right, it's a low friction material, and it provides a direct buffer between the steel shoulder bolt and the aluminum outer hinge pieces. So we don't have to worry about galvanic corrosion because the metals aren't touching each other. We don't have to worry about cold welding because, again, the metals aren't touching each other. There's no ball bearings to kind of worry about getting out of alignment or dimpling or denting the bearing race, so we don't need to use hardened materials. Assembly should be a lot easier because, again, we're not dealing with those tiny little ball bearings. And frankly, it's just a better design. Like a ball bearing style rotary mechanism is good for when you're doing lots and lots of revolutions. It's a low friction thing for high revolution or high RPM applications. But we don't need it for this application. We're just deploying, the solar panels once and then it stays open. So we don't really need the benefits of a low friction ball bearing race when a simple pin spacer would work. Folks seem to enjoy when I went through the toolpaths and cam for the robot 5-axis prototyping video. So I figured I'd show you at least one of the parts here and how it was manufactured. So the setup is pretty straightforward. We've got a square piece of stock with the part kind of positioned near the top, held in a vise. First main operation is a roughing toolpath just to clear out the majority of the material. Then we come in with a finishing tool to take care of this outer contour. Then we come around to the side of the part and drill, deburr, and tap this small hole. This is an M1.6, so it's a really tiny little hole. And the reason we're doing it now, as opposed to later, is that I would like to drill and tap it while there's still a lot of material in the part. So we haven't removed much material. Whereas if we did it later, when we've removed this intersection, there's more of a chance for this outer hinge bit to flex while we're tapping. And M1.6s are already very fragile, so I'd prefer not to break a tap in this hole. So we do it now while everything's nice and stiff. With the sensitive tap done, we can come back in with another adaptive, and this will clear out the stuff in the middle and some of the stuff down here below. We'll do an adaptive from the side to help clear out this little pocket, and the through hole, we'll bore it to size so it's an accurate size. This isn't a critical feature because it's really just the countersink for the bolt, so it doesn't need to be super tight tolerance, but when possible, it's easy to bore stuff, so go for it. We'll do an adaptive to clear out these pockets. These are just the light weighting pockets, just to remove some extra mass. And that's done with a 1mm end mill. We'll come in with a finishing end mill that's designed for making flat faces, and we'll face off this top section here just for aesthetics. Then we rotate around and do another adaptive where we're clearing out kind of the bulk of the material that's underneath the hinge. And we're doing this because it will make some of the future operations easier if there's not material down here. So some of the contours have kind of curved edges that are only accessible, like this contour here is challenging to hit with an end mill if there's material underneath the part. And so this adaptive is clearing that out so that we can access these edges. But you'll note that we waited a really long time to clear out this material because the part will be considerably weaker once we remove it. Now there's like this large overhang, it'll want to bounce around. So we don't clear this material out until the very last minute because it's adding stiffness to the part for the other operations. With that gone, we can come in and do a quick contour to clean up these edges, rotate around and do this curved profile that I just talked about. Ditto on the other side, take care of this curved profile. And you'll note that these curved profiles are important. They're here for a reason, not just aesthetics. This side of the hinge is flat because it is used as a stop. So you can see here, this is the hard stop to keep the hinge from opening past 180. So this needs to be a flat on flat surface basically. Whereas the other side, I guess this doesn't need to be curved. It could be flat too, but this is what it is, aesthetics. It looks nicer. We rotate through here and clean up this inside face and this inside face. We'll rotate around the top and help clear out some of this material along this side wall. And then we walk in with a smaller tool and clean up these corners. So the reason I did it this way, so this is a 1/8 inch end mill. So it's pretty big. We don't have to really worry about it breaking. So it removes the bulk of the material. And then we come in with the small 1mm tool to do the final passes to clean up these internal fillets. Once most of the material is gone, there's very little chance of it breaking now, and it can do just kind of the final cleanup pass. But I should note that these fillets were chosen, let's see, that's the diameter. Diameter is 2mm. I know I'm coming in with a 1mm tool, so these fillets were chosen to be sufficiently large that we wouldn't really have a problem with a small tool. So it could have been a smaller fillet, but then we run a bigger chance of having chatter or breakage in the corner. So in this case, it was chosen to be sufficiently large that we just don't even need to worry about it. Okay, and now it's basically just cleanup. So we come over to these pockets. We do a contour to clean up the outer walls, run a flat tool path to finish the flat surface at the bottom. We clean out this slot. And I didn't mention it before, this slot is here for holding basically the legs of the torsion spring. If you don't have it, like on one of my design iterations, the spring just kind of moves all over the place. It's not really well constrained. So putting a thin slot in is important to keep the torsion spring from moving around. Then we drill these two holes, deburr them, and come in and tap them. These are M2s, and these will be the holes that you'd use to attach to like the solar panels or whatever your deployable is. Then finally, we do a big 5-axis deburr path to take care of all the edges that we can reach, just to minimize how much deburring we have to do by hand later. Come in with a cutoff wheel and slice it off. And just like in the 5-axis prototyping video, you can see that I designed this part so that it has no real features on one of the sides. This bottom side is completely flat, and that was done so that we can come in with a cutoff saw and just saw it right off so that we don't need a second operation. It's a one and done on the 5-axis machine. I usually like to toss the part into a tumbler or like a magnetic pin deburr, let it run for 20-30 minutes, and that just helps take care of any of the burrs that maybe we didn't get on the machine, or help clean up some surface finishes in places where maybe it wasn't quite as good as I'd hoped. And that basically just leaves us with assembly. This is very similar to the last ball bearing hinge, just a lot easier. The torsion spring is lapped and cleaned to make it less crunchy. We coat the various surfaces with tungsten disulfide and then a thin layer of vacuum grease. And then we just insert the bushings into the inner hinge and thread the shoulder bolt through the middle with the torsion spring in place and tighten it all up. And that's it. And I have to say, the feel of this bushing hinge is much, much better than the ball bearings. It's a lot smoother, it's not crunchy, it has kind of a nice feel to it when it opens and locks into place. And frankly, this is just a better design than all the ball bearings. Even though they're very clever designs, I think, the juice wasn't worth the squeeze. We'll just put it that way. It was way too much effort for not really a market improvement, and in some cases a little bit worse. And something like this would probably be much more robust in a space sort of situation. Now, that's not to say it's perfect. There is one major flaw again, and that's the thermal coefficient problem that I mentioned on the last hinge. Again, we've got a steel shoulder bolt that's holding an aluminum structure together. And so as the aluminum grows, we might run into issues here. The easiest way to deal with that, I think, is either put a little bit more tolerance between the shoulder bolt and the shoulder of the aluminum part. So leave some spacing right here so that it has space to grow. I think that would be fine. The next easiest thing to do would be add a little more space to this pocket here and put in like a wave spring, something that just provides a little bit of cushion and can take up the slack as things are growing. That would be pretty straightforward. The only real problem is that this is such a small size. This diameter here is only 5 millimeters. They don't really make wave springs that small, so we'd have to make our own wave spring, but that would be relatively doable without too much hassle. Another thermal issue that we would want to just keep an eye on, I don't think it's a problem based on some napkin math that I've run, but we've got steel, PEEK, aluminum, kind of in a sandwich. But we'd want to officially run the math and make sure there's enough spacing between the aluminum and the PEEK and the steel that they don't bind as they grow at different rates. But otherwise, I am pretty happy with this design. I think it's a neat little hinge. It's certainly fun to play with. And you can imagine mass manufacturing these, making a dozen or 2 dozen without a whole lot of hassle. Whoever had to assemble them wouldn't hate their life like they would with the ball bearing design. So I think this would be the winner. Next steps for something like this would be to make a couple of them and then start subjecting them to functional tests. So putting them on heating and cooling blocks to see how it reacts at 80 degrees Celsius or negative 20 degrees Celsius. Eventually, you would also want to run vibration testing on this. So close it up so that it's in its like stowed position and throw it on a vibration table and shake the bejesus out of it and see if it opens, if it actuates after you've shaken it a bunch. And that will help tease out, is your Loctite sufficient to keep the shoulder bolt in place, or does it work loose? Are the slots for the torsion spring the right size, or does it pop loose under vibration loads? Is it strong enough? Maybe this is just too weak of a structure and it'll just break under high enough vibration holding a large solar panel. Well, apologies for the different change of location. My shop is a total disaster right now. I'm working on a project that's kind of taken over a bunch of stuff, and there's a lot of things going on right now in the shop unrelated to projects, just in my personal life. So things are a bit chaotic and hectic right now, which is why we're doing it in my office, and it was a little less scripted than usual. I found the exercise of trying to think through the ramifications of space and like what that does to a design to be really interesting and enlightening for me personally. Because again, you always hear that space is hard, and like it makes sense that space is hard because you have to make rocket ships and like engines and all that stuff seems hard. But it's the little things too that end up being difficult, like making a hinge. No one thinks a hinge is hard until you actually have to think about, oh, well, how does a hinge survive and operate in space with all of these really unique constraints? and then understanding that this level of design needs to go into every component of a spacecraft. And you can quickly understand why people say space is hard, and it's frankly kind of amazing that anything works at all in space. So, yep, that's all I've got for you. Thanks for watching. I hope this was interesting, and I'll see y'all next time.